Hello everyone. In this video we are going to discuss the numerical from your unit number 1, that is vector analysis, and within this numerical we are going to make use of the property of divergence as well as the property of the curl of a given vector. So how to use that one, that we will see this one. And if you have any queries, you can drop me a mail onto my this email ID, and I will try to get back you as soon as possible. Okay, so we will begin with what is to be done within this numerical. Now in this numerical we are given with some vector g, which is basically in terms of rectangular or Cartesian coordinate system, since it is with the ax, ay and az component, and we have to show whether it is both, that is irrotational, as well as it should be a solenoidal field. So what is that one? So it is associated that your given vector field is said to be irrotational or potential or conservative if we have its divergence is equals to 0. So we have given with this vector g, and if we are going to prove this, that vector g, curl of that vector g is equals to 0, so we can say that vector field is to be irrotational. And second part is that they have asked us to show that your given vector is a solenoidal field. So given vector field is said to be solenoidal or divergenceless if we have that divergence of that given vector is equals to 0. So the thing is that we have to show that del cross g is equals to 0, as well as we have to show that del dot g is equals to 0. So this is what we are going to say to be the irrotational, as well as we are going to say this to be the solenoidal field if we have the divergence is equals to 0. So we will begin with that one. For your reference purpose, I am writing this note over here that a given vector field is said to be irrotational, or it is said to be potential, or it is said to be conservative. In which case, if we have the curl of a given vector, so we are given with vector g over here. So if we have that curl of given vector is equals to 0. So these are the one and the same thing. So it is not necessary that you should have this irrotational word over there. They can also say you that show that it is both show that it is potential, or whether it is find out whether it is conservative. So these are the one and the same thing. So irrotational and potential and conservative vector fields are what? The vector fields having the curl with 0 value. So these are what about the that conservative fields, or you can say the irrotational fields. Now we will begin with the proof of this numerical. You just write it somewhere. As we have seen earlier, a vector field is said to be irrotational field if the curl of that given vector field is equals to 0. Now this given vector is in rectangular coordinate system. So we have the curl for that rectangular coordinate system. So we are going to write that del cross G is equals to what? Curl of the rectangular coordinate system. And what we have that to be? So that will be the determinant of this one. That is Ax cap, Ay cap, and this Az cap. Then over here will be what now? D by dx, d by dy, and then d by dz, having magnitudes along magnitudes with respect to x, y, and z for your given vector g. This is the curl of your given vector g. Now we are going to put that values over there. So rewrite that one again. Ax cap. You can skip this previous step if you are expert with that one. You can directly go with this. Curl of given vector is this one, d by dx, d by dy, and then d by dz. For your reference purpose, I have written this one. So what is magnitude along that x direction? So we have that magnitude to be what? Yz. Magnitude along that ay direction. Magnitude along y direction is what? That is xz. And what about magnitude along z direction? We have that to be the xy. Okay. Now simplify this determinant. So what will be the simplification? Very firstly, you will find that Ax cap is as it is. Now this d by dy, of your this component, that is xy, minus d by dz, of your this xz component, then plus ay, then d by dx, sorry, d by dz over here. This is how it works. d by dz of this yz minus d by dx of this xy, then plus az component, then this d by dx of this xz minus d by dy of this yz, dy dy of this yz. See, some people also say that to be the Dava operator. Okay, so now we are going to simplify that one. This operator, d by dx and d by dy and this d by dz. So it is also said to be a Dava operator. Okay, how you are comfortable with that? You can pronounce that one. So that doesn't matter. What matters is your correct answer. Okay, so this one, ax cap. Now simplify that one. So derivative of this bracket, very first bracket with respect to y is what? We have that to be the x. Derivative of second bracket with respect to z is what? We have that to be the x again. Then plus ay. Now derivative of this bracket with respect to z is what? We have that to be the y. And derivative of this bracket with respect to x, that is to be y plus az. Derivative of this bracket with respect to x is again z, and derivative of this bracket with respect to y is what? We have that to be the z. Okay. Now if you simplify that one, so what is your observation? We have found that the curl of your given vector g, and that is equals to what? That is equals to 0. So this is the proof that your given vector is irrotational if we have the curl of a given vector is equals to 0. So this is the very first part of the numerical. Now we will move on to the second part of the numerical. Okay, for your reference purpose, I am writing this note over here, which state that a given vector field is said to be solenoidal or divergence-less. So these are the one and the same thing. Divergence-less or solenoidal field is what? If the divergence of your given vector field is equals to 0. So these are the one and the same thing. So if it is given over here that find whether the given system is divergence-less. So then in that case again we have to prove that del dot g cap is equals to 0. Okay, so this is the important note. Write it somewhere, and it is not necessary that you should write it in your examination. Okay, so I am going to rub it out and then we are going to start with the numerical. So we have written it over here again that a given vector field is said to be the solenoidal or divergence-less if we have the divergence of the given vector field is equals to 0. Now since this given vector is expressed in terms of the rectangular or Cartesian coordinate system, so we are going to write what is the divergence of your given vector g in terms of the rectangular system. So what we have that to be, so that is equals to d by dx of your magnitude along x direction of your given vector g, then d by dy of magnitude along y for your given vector g, and that is again plus d by dz of magnitude along z direction for your given vector g. Now simply put that values over there. So what is the magnitude along the x direction for your given vector g? So that is equals to what? Yz. So d by dx of your yz, then d by dy of your magnitude of given vector g in y direction is equals to what? Xz, and we have the third component, that is d by dz of your magnitude of given vector g in the az direction. So that is what? That is xy. Now differentiate that one with respect to that given this. So we have that to be what? D by dx of yz. So since there is absence of x term, so this will be 0. Now here in this case d by dy of xz, there is no y component, so that will be 0 again, and d by dz of this xy. So since there is no z component, so again that will be equals to 0. So we are left with what now? So we have proved that your given vector field is said to be the solenoidal or divergence-less if we have that divergence of given vector g here in this case that is equals to 0. So this is the proof for your numerical. Okay. So write that note somewhere and mug up that one, practice that one. So this is the end of your numerical, and you can appreciate my efforts by hitting the like button. Okay. Thank you.